Now that we've covered a lot of the normal scenarios with typical DNS stimulus and response, I want to get into abnormal stimulus and response that you may observe in relation to DNS. And I'll tell you, there's a lot of abnormal DNS stimulus and response that can occur. We're a little limited on time here. I don't want to spend hours and hours on this, but I want to cover some of the most common things I think you'll see and tell you a little bit about what they'll look like and how to spot them. Now, some of those things are related to how DNS itself can be abused, and some of them are related to the source and destinations oddities of where DNS traffic comes from. So I want to focus on that just a little bit here, and we'll start by picking up our conversation from the last section on zone transfers and talk about malicious zone transfers. Obviously, zone transfer is an interesting thing in that you're talking about transferring the entirety of DNS records from a zone from one host to another, and that's kind of a gold mine, right? That's a lot of information. You're talking about a mapping of every host in your network, the IP addresses and the DNS names. And those DNS names are often pretty descriptive, right? Like we often name servers file server 1 or domain controller 2. So that's useful information, especially useful for a bad guy. So it's not unheard of that bad guys attempt to perform zone transfers against our DNS servers. And DNS servers traditionally used to be configured such that they would allow zone transfers from anywhere by default. Now, that's not the case anymore most of the time. Most DNS servers are configured to where they will only allow zone transfers to specific hosts that you identify. You have to manually input those by default. And so you want to allow that from primaries to backups and things of that nature. But you want to be secure in the way that you don't allow DNS zone transfers to just anybody out, either within your network or on the internet. So there are a couple scenarios here that you want to look for that could be potentially troublesome. One of those is a zone transfer request from a random internal workstation, right? So if you have, you should know on your network where DNS AXFRs should be coming from and IXFRs where they should be coming from, right? They should come from DNS servers to other DNS servers. But if you see a random workstation, try to perform a full lookup for a DNS server. This one here, this example says chrissanders.org, but it would really be for whatever your internal domain is called. If you see that, that may be worrisome. It may be the sign of an attacker who's gotten into the network and is attempting to expand their control and do some internal reconnaissance. So if I see a full transfer on my network from a workstation, that is weird to me and I want to dig into that. The other scenario are DNS servers that are misconfigured and publicly accessible, right? Many of our DNS servers are publicly accessible because, especially those of us who have public-facing infrastructure, and we need to provide DNS services so people can find it. If we host our own DNS servers, that is. If those are publicly accessible and they're configured to allow zone transfers from anywhere, and you see external IP addresses performing zone transfers, they're basically enumerating your network, right? And not only that, they're probably enumerating some of your internal assets of your network as well. So external IPs doing full transfers from your DNS server may not be something you want. There are some use cases where maybe that's okay, but probably not something you want unless it's specified. So the key thing here, this isn't a DNS architecture lecture, but you want to lock down who can perform zone transfers against your DNS infrastructure. And even if you don't have it locked down, or even if you do have it locked down, you still want to monitor for this and monitor for zone transfers. Even if the transfer doesn't work, the attempts in themselves are anomalous. If a random internal workstation attempts a zone transfer on my network, even if my system is not configured to respond to it, the attempt itself is anomalous, right? So that's something we want to look at and keep in mind when we're thinking about abnormal stimulus and response for DNS and malicious zone transfers. The second type of abnormal stimulus and response for DNS I want to talk about is a concept called fast flux. Now in this case, we have a DNS client and a DNS server, and we performed a DNS request for chrissanders.org. Now remember, when the DNS reply comes back, it comes back with a field called TTL, and that tells the client how long the value is valid for, right? How long that mapping exists before we need to go out and get a new one. So in this case, in our example, we've gotten a response that says chrissanders.org is at 42.51.51.12, which may be a valid IP address, but of interest here is the TTL is really low. It's only a minute, right? And that's not a long time. That's not a long time to hold a DNS response. Now, here's where things get interesting. After a minute, my client is going to send another request to re-resolve this information. And you know what's going to be sent back? It's actually a different IP address, 64.141.32.141, with another really low TTL. That's interesting. That's a technique we call fast flux. It's often used by attackers to protect their infrastructure. Think of it this way. I'm going to deploy malware onto your system as an attacker, and instead of hard coding an IP address in there, let's look at it this way. If I hard code my IP address in there, then you could just block that IP address, right? You could just block it on your firewall, and that malware will never work. It's completely useless. But if instead, what if I perform my malware to actually point to a DNS name? Let's say chrissanders.org was the evil name I programmed into my malware. Well, I can configure the DNS server, since I'm responsible for that zone, to have a really low TTL of 1 minute and configure it with hundreds of IP addresses, thousands of IP addresses, all these different IP addresses that are hosting malicious content. Say this malware is a dropper and it's meant to download additional malware. Or maybe it's better yet, let's say it's a C2, it's command and control, and I want to send commands, or I want it to check into commands from this system. If I hard code the IP address and you block it, I'm done. I can't do anything else. If I put a DNS name into the malware and set a really low TTL, not only can you not just block a single IP address, it's going to be changing every few minutes. So whereas you might see this the first couple times and block those IP addresses, you're not going to be able to block them all. You're actually going to have to address the root cause of the issue, which is the malware itself. Now humans, most of them in a good SOC are going to address that eventually, but this technique is going to allow the malware to run longer. And if you have automated processes attempting to doing this blocking, they may block the first IP address or the second IP address. Maybe they're in a known bad list, but they might not know about the third IP address or the fourth one or the 18th one or the 3042nd one. So this is a technique that bad guys use to make their infrastructure more resilient by taking advantage of this TTL field in DNS traffic, by setting that really low, using DNS names in their malware and in their configurations, and then having an army of IP addresses that are hosting malicious content, etc. So this is abnormal fast flux, and you'll know this when you see, number one, a lot of DNS requests from a client to the same server, and also DNS requests with a really low TTL value that are coming back with a bunch of different IP addresses. The next abnormal stimulus and response we'll talk about relates to ISPs manipulating or kind of going against the DNS RFC as far as how responses are supposed to be formed. So let's take a look at this example. We have a DNS client and we have an ISP's DNS server. Generally, most people are going to use upstream, at least, their DNS, their ISP's DNS server. That may be what you're using, or maybe not. Maybe you're using a public DNS from another ISP, like a 4.2.2.1 or an 8.8.8.8, something like that. But generally, most people use the upstream DNS server of their ISP. Now, the bad thing about ISPs is they have a little bit of leeway in terms of how they interact with your traffic, and this is an example of something they do which is not really quite preferable. In this case, we have our client, our server, and our client is going to initiate a DNS query to the ISP's DNS server. Now, this may be direct, it may be going through another server, it doesn't really matter. All that you need to know is that a client has initiated it, and it's eventually being responded to by the ISP's DNS server. Now, in this case, I listed NX domain here. Of course, that's shorthand for a non-existent domain or a domain not found. So we're making a query to a domain that does not exist, right? And of course, maybe we don't know that's happening, but for this exercise, we'll say that for certain we know that that domain does not exist in this DNS query. Now, what we would expect to get back is an NX domain response from the ISP's DNS server, right? That's how DNS works. That's the example we talked through with normal stimulus and response. If you try to query for a DNS name that doesn't exist, the authoritative server will respond and say that that name is not found, and then the client will have to either try again or you'll have to re-enter the domain again, whatever's going on the application side. However, in this case, that's not what's going to happen. The ISP is actually going to respond to this query, and they're going to respond to it with an IP address, but it's going to be their own IP address. So anytime they receive a query for a non-existent domain, they're going to respond with an IP address that points you to something in their infrastructure. And from my experience, that's usually a search page. They'll take the IP address and plug it into that search page, and that's what you'll end up getting back, especially if you're using a browser, right? Is instead of going to www.nonexistentdomain.com, you're actually going to get redirected essentially to ispsearchpage.com/search for whatever IP address or whatever domain you looked for. Now, that's not a good thing, right? That's not a bad thing. We don't like our traffic being redirected really in any case unless it's something we set up. There's an opportunity for information leakage here. Think about if you're using a web browser and you try to go to an internal domain and you're passing some variables to it, but you mess up the domain. Well, those variables are now going to be redirected to that HTTP search page, right? Because what's going to happen is the web client, in this case, the HTTP browser, is actually going to try to initiate a TCP SYN connection out to that, establish a session, and browse to it. So that's what we see most of the time is users browsing to a website. They'll mess up the domain. They'll end up getting redirected to the ISP search page for that domain. Furthermore, these search pages, more often than not, tend to have advertisements on them. And anytime you are going to a page that has advertisements on and it's participating in an ad network, there is a chance that malicious ads could be served through that. We see that all the time. That's how exploit kits proliferate. Ad networks are kind of a disaster from a security perspective. So this introduces more of that into your network, which is certainly undesirable. So this is kind of the abnormal stimulus and response related to how ISPs can hijack your DNS by not fully complying to the standard on how they should respond to domains in which the response should be non-existent or NX domain. I've opened up a file now called DNS ISP hijack to demonstrate the concept I just talked about. Now I'm going to go through this at a very high level. I'm not going to go through it in too much depth because you have a lab exercise where you'll use this capture file. But if I go too fast, don't worry. Remember, every capture file I use in this course is one that you have available to you to go through kind of at your own pace. Now, this one's pretty straightforward and illustrates the concept we just talked about. Here at the top, we see I'm making a DNS query from 172.16.16.170 to 4.2.2.1. That's a public DNS server. I believe it's provided by L3. In this case, I make a standard query for an A record for a very long and nonsensical URL, another one where I basically mash my face against the keyboard to see what would happen. In this case, I did verify this domain definitely does not exist. Of course, someone watching this course may go and register it now, but as of doing this domain does not exist. Now, what we would expect to see here is a response from a DNS server that says NX domain not found. And matter of fact, let's go ahead and click into the second packet here, and we would see that here in this, we've expanded DNS, and we're going to click into flags. If we go into flags, we should see that right here under reply code, right? I believe it's the third bit from the left here that will tell you if that's set to 1, then we have no domain found, NX domain, and that should be it. However, we don't have that here, so that's trouble sign number 1. If I close this, we see we also have answers. Remember, the things we have when we don't have a response are we have that error code for NX domain. We don't have answers. In this case, we have answers, so that's troublesome. We go down to answers, and sure enough, we see we have 2 IP addresses supplied. So that's very odd, right? For a domain we know not to exist, we're actually getting told it's existing, and it points to 2 different IP addresses. Sure enough, if you look up these IP addresses, you'll see they're associated with L3 communications. And notice this 104.239.213.7. Immediately following, we make an HTTP request out to 104.239.213.7. So we're actually communicating with that IP address. Now, you're going to have a lab exercise in a minute where I want you to dig into this a little bit further, actually see what you're browsing to and kind of rebuild the story of what's going on in this capture. But for the most part, just looking at the DNS traffic, you can see, again, we're making a query to a domain that I know for a fact doesn't exist. The ISP's DNS server is responding to it, and that's an example of an ISP doing this ISP hijacking that many of them do. Many of the big boys do this. I think Charter's done it, Comcast, L3, of course. I believe there's a Wikipedia page on DNS hijacking by ISPs that actually maintains a list of that. But this is pretty common, and you can definitely test this out on your own and try browsing to a non-existent domain, maybe the one on the screen here, and seeing if you get similar type responses back. The last abnormal S&R for DNS I want to cover is the concept of spoofed responses. And this is really important to consider when we're talking about UDP-based DNS traffic, right? UDP is not a session-aware protocol. And when you're using protocols that are not session-aware, you're susceptible to people who are sniffing the wire and spoofing responses, right? So let's say we have a DNS client. He's sending a DNS query to a DNS server. Now, what the client workstation doesn't know is that there's actually an attacker on the network. And this may be on your corporate network, or maybe it's at a Starbucks or some public location, something like that. There's an attacker on this network, and he's sitting there and he's running a rogue DNS server on his system or some specialized application for DNS spoofing. Now, if the rogue DNS server is listening to the client and its communications, it can see this DNS query. It can see it going out. And if I can see the DNS query, I can sure as heck respond to it, right? The only thing I really need to respond to that in this case is the transaction ID number, and then I should be able to respond to that spoofing the address of the DNS server. Remember, I don't care if the DNS client needs to be able to communicate with me. I just want to poison its DNS cache. I want to poison it with a bad message. Let's say the DNS client is querying for google.com. Well, if I tell it google.com is actually at my IP address, at the IP address of whatever the rogue DNS server is, or another malicious host, I can actually redirect that client to go download malware somewhere, right? That's pretty cool, or at least from the attacker perspective. So all the rogue DNS server needs to do here is respond faster than the other DNS server. It's a race condition, and if the rogue DNS server responds quickly, it can get that response in first and get that information cached. Now, that brings up the question of what happens to the DNS server's response to the legitimate DNS server. Well, that's a good question, and that's going to vary a little bit depending upon operating system architecture. But in many cases, when you have this going on, the rogue DNS server is actually going to attempt to perform a denial of service against the DNS server itself so that it can slow down its communication and ensure that it wins the race condition, right? Because that's the key thing here, is winning that race condition. So this is a very simplified discussion of DNS spoofing, and it only works with UDP. But you kind of get the concept here. It's similar to what we discussed with rogue DHCP servers, in which he who responds fastest when talking on UDP wins the race and can cause bad things to happen. So worth keeping a note, this is just another example of abnormal stimulus and response for DNS. So that's going to bring us to the end of our DNS discussion. We've gone through a lot of stuff here. DNS is pretty fun. But that said, we've really almost only scratched the surface. There's a lot of nuance to DNS. I've picked these specific topics because I think if you learn and understand all the things we talk about here, you can really understand most of DNS and apply it to the framework we've kind of provided. DNS can get big. There's a lot of different query types, a lot of different nuance, a lot of different implementations of it. But really, we've covered a lot of the main things and enough that you should be able to identify most normal and abnormal stimulus and response and apply it to these frameworks. So with that said, definitely take a moment to examine the labs we have for DNS if you haven't already, because they'll give you a good chance to practice dissecting DNS traffic using whatever protocol analyzer that makes sense and that you want to use.